Welcome back. So, till now we have seen many problems on the laminar and turbulent boundary layer. This is a similar type of question that we did last time, but instead this has some values in it. So, we have been given the thickness of the boundary layer, okay. We have been given the length of the plate, we have been given how much wide is it, and what is the capital U it is given, the viscosity is given. So, what I am going to do is you are going to solve this particular problem, okay. I mean not in the entire detail, but I will outline the procedure. So, velocity profile is given, right. So, I will definitely write what is given. So, capital U by small u by capital U is given 3 by 2. So, this is the sorry 1 by 2 . Okay. And we also have been given that the length of the plate is 2 meter, B is 1.4 meter, okay. And the capital U is also given as 200 into 10 to the power minus 3 meters per second, and mu is also given as 0.001 Newton meter per second squared. So, what we do when x is equal to 1.5 meter, Reynolds number at x is going to be rho ux by mu. Okay. All right. So, after you substitute all these value, it will come 3 into 10 to the power 5. So, basically it is laminar, okay. And for the laminar boundary layer, delta we know 4.64x under root Re at x, and after substituting this x and Re, what we get is 0.013 meter. All right. So, this is the boundary layer thickness. And for that we already have derived 3 by 2 mu u by delta, and after substituting in the values you will get 0.0231 Newton per meter square. This is simply substituting in the values. And similar, if we put in Fd, the drag force that we have derived in the last thing, so it will come out to be 0.114 Newton. You should verify it actually, okay. Just substitute in the values. Because this was on one side, so total is going to be, total force is, there are two sides 2 Fd, so it is going to be 0.229 Newton, okay. All right. So, this is the same question, but with numerical values. So, I will go now. We solve this question. This is typically an interesting one, a sort of a derivation of the of the turbulent boundary layer von Karman analysis. So, this one I will go so that you are able to follow. So, okay, let me first go and tell you what the question is. It says that the velocity profile for turbulent boundary layer, so the velocity profile for turbulent boundary layer is given by 1/7th power law. Obtain an expression for drag force and the average coefficient of drag in terms of Reynolds number. Actually, we have already seen those equations without going into too much detail, but here we can derive it. The wall shear stress for turbulent shear boundary layer is given as, so tau naught is given, okay. Okay. So, how to attack this problem? We simply go white screen. So, we write the things that are given. So, u by capital U is given as y by delta to the power 1 by 7, where tau naught is 0.0225 rho u square into mu by rho u delta to the power 1 by 4. So, we have seen for turbulent boundary layer, delta is given as 0.376 x into Re at x to the power minus 0.2, okay, or delta is given as 0.376 x divided by Re x to the power 0.2, right. So, substituting this delta into the shear stress, if you substitute this, all right, so tau naught, tau naught will be 0.0225 rho capital U square into mu by rho u, and in place of delta we put this, all right. So, delta will be 0.376 x into Re x to the power 1 by 5 and to the power 1 by 4. On rearranging, we can get tau is equal to, so there are some steps which you will have to do, 0.0287. Okay, I will not miss those steps because that might be more. So, this will become 0.0225 divided by, this will come out 0.376 to the power 1 by 4 rho capital U square u by rho u to the power 1 by 4 into rho u x by nu to the power 1 by 5 to the power 1 by 4 into 1 to the power x to the power 1 by 4, okay. So, if you multiply x here and x here, and on rearrangement, this expression actually can give you tau naught is equal to 0.0287 rho capital U square into 1 by Re to the power x 4 by 5 to the power 1 by 5. Or tau naught is equal to 0.0287 rho capital U square divided by Re to the power x into 1 by 5, okay. So, now Fd is equal to integral 0 to L tau naught b dx. If you substitute this and integrate it, we are going to get, we already have this tau naught in terms of Reynolds number to the power 1 by 5, So, just to be to make it complete, 0 to L, tau naught can be written as 0.0287 rho capital U square divided by RE x to the power 1 by 5 B dx. Now, RE should be written in terms of UX, I mean the usual numbers, and FD on simplification will come out to be 0.036 into rho capital U square BL divided by REL to the power 1 by 5, and CD in the end will be FD divided by half rho A U square. FD will be this thing, A is going to be B into L for example. Therefore, CD is going to be 0.072 divided by RE to the power L to the power 1 by 5. All right. Same way of solution, so no difference. So, if you get a velocity profile, you can proceed it in a similar way, given that for a turbulent flow the shear stress profile is given. All right. So, now we have to study about something called the boundary layer separation. What is boundary layer separation? So, we have seen the mechanism of the formation of the boundary layer as such. All right. So, along the length of the solid body, the thickness of the boundary layer increases, that we have already seen, and the fluid layer next to the solid surface has to do work against the surface friction. That is true, and this work is done at the expense of the kinetic energy. All right. The loss of the kinetic energy is recovered from the immediate fluid layer in contact through the momentum exchange. Hence, the velocity of the layer goes on decreasing. So, along the length of the body, a certain stage may come when the kinetic energy is no longer sufficient to overcome the frictional resistance. All right. I mean, the kinetic energy transferred from the upper layer to the below layer, for example, is no longer sufficient to overcome the frictional resistance. In that case, the boundary layer will be separated from the surface, and this is called the boundary layer separation. Okay. The point on the body at which the boundary layer is on the verge of separation is called the point of separation. The flow reversal can occur at the downstream point of the separation. All right. So, this is what this phenomena is. I mean, this is what exactly is this phenomena. Now, we are going to see what the effect of pressure gradient boundary layer separation is. So, what is a favorable pressure gradient? That the pressure dP dx is less than 0. So, pressure at one point, if it is higher than the second point, then the flow will occur. So, that is the favorable pressure gradient. In this case, the flow is accelerated by the pressure forces, hence the boundary layer thickness keeps thin and hugs closely to the wall, okay, in the favorable pressure gradient. However, in adverse pressure gradient, where dP dx is greater than 0, the outer flow is deaccelerated by the pressure forces, because the pressure forces will act in the opposite direction because of the adverse pressure gradient. In that case, the boundary layer is usually thicker and does not remain very close to the wall. Therefore, the boundary layer separate from the wall, which progresses into the main flow, and this is the flow reversal. You see, this is the point of separation. All right. So, comparison of boundary layer profile shape as a function of pressure gradient. dP dx is minus u du dx. Okay. A is a favorable case, you see. B is 0, this one. C is mild adverse, because this is a pressure gradient, a different pressure gradient, you see. D is critical, all right, and the fourth is large adverse, you see the pressure gradient dP dx, all right. All right. So, the separation is determined from this, where the separation point is going to be is determined from the condition du by dy at y is equal to 0 is equal to 0, all right. So, for a given velocity profile, if du by dy at y is equal to 0 is less than 0, this means that the flow has already separated, and if it is equal to 0, it is on the verge of separation, and if it is greater than 0, this means it will not separate, the flow is attached with the surface, all right, because du by dy at y is equal to 0, the shear stress, that is the main thing. You know, if it is less than 0, that means flow has already separated, because so now we are going to solve two problems related to that. One is for the given velocity profiles, determine whether the boundary layer has separated or on the verge of separation. So, these are the three velocity profiles. Very simple. In these velocity profile, we need to calculate du by dy at y is equal to 0. Simply, if it is negative, it has separated. If it has not, then if it is 0, then it is on the verge of separation. So, we are going to have this white screen. So, let us say for part 1 actually, u small u by capital U is equal to 2 into y by delta minus y by delta whole square. Okay. So, let us do du by dy. So, this is going to be 2 u by delta minus 2 y u by delta square. Okay. And du by dy at y is equal to 0 will give us 2 u by delta, which is greater than 0, that means flow is attached, all right. The second velocity profile, where u was u by capital U is minus 2 y by delta plus half y by delta whole cube. Here du by dy is going to be minus 2 u by delta plus 3 u y square by 2 delta cube. At y is equal to 0, du by dy is going to be minus 2 u by delta, which is less than 0, which means separation has occurred. In the third problem, when you do, third problem has u by capital U as 3 by 2 y by delta whole square plus half y by delta whole cube. So, this du by dy is going to be 3 u y by delta square plus 3 u y square by 2 delta cube. So, that means at y is equal to 0, du by dy at y is equal to 0 is 0, all right. So, this is equal to 0, means on verge of separation. All right. So now one more problem. So the velocity distribution in the laminar boundary layer is of the form u by capital U is equal to f of eta plus lambda g of eta, where f of eta is 3 by 2 eta minus eta cube by 2, and g of eta is eta by 4 minus eta square by 2 plus eta cube by 4, and eta is y by delta. Find the value of lambda when the flow is on the verge of separation. So this is an interesting problem. Okay. So what is given to us? U by capital U is equal to f of eta plus lambda g of eta. Okay, where f and f eta and g eta is given. So from the profile, u can be written as capital U f of eta plus u lambda g of eta. Okay, this is equation number 1. So du by dy can be written as du by d eta into d eta by dy. Okay. Or du by d eta can be written as d dy dd. So d eta by dy can be, actually this can be written as d dy of y by lambda into du by d eta. All right, this is here. Or du by dy can be simply written as 1 by lambda into du by d eta. All right, this is without utilizing that, and this is equation number 2. So if we differentiate this 1 with respect to eta, what we get is du by d eta is equal to u d d eta of f of eta plus lambda u d d eta of g of eta. All right, and this will, on putting the values, this will give us du by d eta is equal to, so u 3 by 2 minus 3 eta square by 2, 3 eta square. So I'll just write down again. This du by d eta finally comes out to be capital U 3 by 2 minus 3 eta square by 2 plus lambda u into 1 by 4 minus eta plus 3 eta square by 4, and this equation we call equation number 3. Substitute 3 in 2, and then we get du by dy is equal to u by lambda 3 by 2 minus 3 eta square by 2 plus lambda u by delta into 1 by 4 minus eta plus 3. All right. So when the flow is on verge of separation, this means du by dy is equal to, at y is equal to 0, is 0. All right. So what we do, we put it equal to 0, and what we obtain is u by delta into 3 by 2 plus lambda u by, there are some other steps which I think you must do it, 0 or, all right, u by delta you take common, this will give us 3 by 2 plus lambda by 4 is equal to 0, which implies lambda is equal to minus 6. All right. So for lambda is equal to minus 6, the flow is on the verge of separation, and this is the answer to this question. Okay. All right. So now the control of boundary layer separation, we are proceeding towards the end. So how this boundary layer separation can be controlled? So boundary layer separation is associated with continuous loss of energy. So that means eddy formation is there in the reverse flow region. Okay. Hence separation of boundary is undesirable, and therefore it needs to be stopped. And some methods for preventing the separation of boundary layer includes, these are only some. So if we provide a streamlined profile to the body, or we can supply additional energy from a blower, suction of the slow moving fluid by a suction slot, and rotating the boundary in the direction of the flow are the some of the measures using which the boundary layer separation can be stopped. So this these are the references as usual for the actually entire hydraulic engineering course, and this also concludes our topic on boundary layer analysis. Thank you so much. I'll see you in the next lecture. Bye.